This video explains the evolution of RTP from a supplier of high-performance I/O and fast data acquisition systems to a company that provides the best-in-class, safety, and critical control system. Shown here is the TMR configuration of the RTP3000 TAS. It is a SIL 3 certified system that is state-of-the-art. As you will see, it is based on an innovative architecture, and has been implemented using a multi-processor design. Two objectives preceded the development of this system. First, the architecture should result in a product that is a best-in-class safety system or a critical control system. Second, the functionality that would be essential for RTP to compete effectively needed to be established. What you see here are the three essential capabilities that were chosen. First, it had to cost less, second, it had to run faster, and third, it had to run longer between failures than the existing competition. Also, the hardware should be the best in class regardless whether it is to be used in a safety application or a control application. There should be no change required in the hardware. The operating system should be the only change necessary to compete as a safety or control system. After 4 years of evaluation by Exida and TUV, in 2008 RTP received a SIL 3 certification of the RTP3000 TAS. The non-safety version was released in 2004 and the safety version was released for sale in 2008. The product was also the first system to receive Level 2 cybersecurity per EDSA 300. That happened in 2011, and since then only a few other systems have been able to attain Level 2. The system was also certified to have safety and control applications running in the same hardware at the same time if a customer so requested. It should also be pointed out that the system is a true redundant system and not hot standby. One final note is what RTP refers to as configurable redundancy. For example, input points can be configured as quad redundant, CPUs can be configured as triple redundant, and output points can be configured as dual redundant. As you will see, there are no hard requirements on how the system must be configured. The next thing RTP did was to evaluate what was perceived to be the best systems in the marketplace, and a diagram of one of those systems is shown here. There were many advanced features that we learned based on our evaluation. However, it became clear that there was no way to improve on the numbers already claimed by the competition based on this architecture. Therefore, a completely new approach was required. The approach chosen is shown here, and as you can see is a very different architecture compared to traditional safety systems. There were several objectives that this architecture needed to meet. First, each time a chassis is added there needs to be an increase in compute power. As a result of this requirement, the total processing requirements was divided, and the concept of node and chassis processors evolved. Each time an expansion chassis is added, a chassis processor is also added, resulting in an increase in compute power. This increase in compute power would be split between the requirements to provide fast logic solve scan times, and increased mean time to fail. The final division of processing is shown in the top of the slide. Basically, node functions like logic solving, host communication, and engineering conversions are performed by the node processor. Chassis functions like communicating to the I/O, and field diagnostics are performed by the chassis processor. Second, it should have unlimited online downloads of both logic and configuration changes. Also, hardware should be able to be removed or added while the system is operating, in other words hot swappable. Next, one issue that many customers emphasized as highly important to them was separating the CPUs into multiple chassis instead of all CPUs being in one chassis. Finally, the proof test interval had to significantly increase beyond the typical 18 months of most systems while using no more than 30% of the SIL 3 budget. At the onset of RTP's initiative to enter the safety market, 3 objectives were defined: cost less, run faster, and never stop. The implementation yielded the results shown. A scan rate of 200 passes per second was achieved. Of special interest is the 2,634 years mean time to fail spurious, MTTFS, which is the main component of mean time to fail. The latest technology was used, not only to increase performance but also to reduce cost. A 3-year warranty was also offered. These enhancements allowed RTP to offer not only a very competitive initial purchase price but also a lower cost of ownership. A Markov model was developed by Exida for the first release of the RTP3000 system. The improvement in MTTFS is displayed in the box never stops. These numbers are based on that Markov model. This is a page from the Exida report showing the resultant table based on a Markov model. It can be seen that the original goal of extending the proof test interval to 5 years was met, along with the requirement of keeping the percent of the error budget below 30%. From the Exeter report, developed by Dr. William Goebel, input modules with a single architecture, 1 out of 1, will provide cost-effective inputs with a safety integrity rating of SIL 2. The dual architecture, 1 out of 2, will provide high safety integrity to a rating of SIL 3. The triple architecture, 2 out of 3, is used to provide higher availability of the input subsystem. Diagnostics are primarily provided via comparison in the node processor. Node processor modules can be configured with single, dual, and triple architectures. The single architecture, 1 out of 1, is the base configuration. A dual architecture, 1 out of 2, is used to achieve high safety integrity. A triple architecture, 2 out of 3, is used to achieve both safety integrity and high availability. Comparison diagnostics between the node processors provide high effectiveness fault detection even with transient bit errors and soft failures in small geometry integrated circuits. The approach of using detail comparison instead of extensive self-diagnostics also frees computing power to ensure higher application function performance. Output modules with a single architecture, 1 out of 1D, will provide high safety integrity to a rating of SIL 3 with no redundancy. The dual architecture, 2 out of 2D, is used to provide higher availability for each output subsystem. Single-channel safety integrity is achieved through automatic diagnostics, which will initiate an output shutdown if potentially dangerous failures are detected. The diagnostics are run locally in the output module, in the chassis I/O processor, and in some cases in the node processor. Dr. Goebel goes on to say this combination of safety integrity, high availability, flexibility, and performance sets new levels of expectation among safety PLC users. Pictured at the top is RTP's software offering, NetSuite. A complete explanation of the functions available will be explained in a later video. Shown here are some of the many different combinations of architectures that are possible. Node processors can be located in any chassis or all in the same chassis. The system on the left is a TMR system with the node processors all in one chassis. In the middle is also a TMR system, this time with the processors configured in 3 different chassis. A node can have up to 16 chassis and they can be located remotely using redundant fiber cables. A node can have more than 8,000 I/O points. Up to 99 nodes can exchange information on the host network using peer-to-peer communications. This results in over 800,000 I/O points available for a section of a project. Redundant I/O channels can be configured to be on the same card, on different cards in the same chassis, or on different cards in different chassis. This is referred to as configurable redundancy. As you have seen, the RTP3000 TAS has implemented many advanced features, making it the most advanced safety system available. What may not be so obvious is that by simply changing the operating system, the product can be transformed into a system suitable for critical control applications as well. This is possible because at the onset of this development effort, the requirement was to implement high accuracy, high-speed analog input and output capabilities. This functionality has been common in all of our high-performance data acquisition offerings. Thank you for the time today so that we could explain the process RTP went through to develop a best-in-class safety system. The next video will explain how the already best-in-class numbers were improved as RTP continues its quest to enter the safety market.